Okay, there we go. There we go. Recording is in progress. Okay, so fantastic. So let's have a little look here. We've got lots of great stuff. Fantastic. So yeah, so this is likely to be, okay, very nice. Marie, that's kind of pretty much the full kit and caboodle there. Obviously, it's probably some observation and then through trial and error. So she's kind of basically learned by doing, right? And I see lots of trial and error, that kind of stuff. Exploratory, yes. So she's learned by imitating and by exploring and doing that kind of stuff. Okay, fantastic. All right, one final question. So she didn't learn how to do this using language. She did learn how to do this using sort of trial and error, exploring, maybe some observation. But what is this little girl doing that's so fascinating from an educational perspective right now in the picture that we see on the screen here? What is she doing that is so interesting from that educational perspective right at this moment? She's replicating. We can take a minute and just think about it. All right, there's the terms I'm going for. Fantastic. She is transferring her learning from one domain to another. Very interesting. For those of you who've taught mathematics, which I'm sure is probably a lot of people on this call, transfer is a very, very difficult thing to get kids to do, to the point where, you know, certainly teaching middle or high school mathematics, the idea that you might teach kids something in one domain and then they try and apply it somewhere else almost feels like the holy grail. And it feels like, wow, that's just obviously not a natural thing to do. It's so difficult to try and get kids to do that. And yet here's this little girl who is just naturally trying to transfer her knowledge onto another domain. And what this really speaks to is it comes down to the way that she's learned how to do this. She learned how to do this for herself. She owned the process of that learning through trial and error, through exploring, et cetera, et cetera. And she has literally built a schema in her brain of how this works. And it turns out that this desire to then to try and apply those schemas that we have in our brains, the sort of neural networks that we build up that form our learning, it's actually a completely innate and natural thing to try and apply them somewhere else. Unfortunately, when we learn without really building these schemas for ourselves, yeah, transferring that knowledge somewhere else is not something that happens naturally. So what we're observing here is kind of almost a very natural learning process in action. And of course, it begs the question that if this is possible, if it's possible to get learning to happen like this in such a natural way, what if mathematics could be taught in a similar way that matches the way that the brain actually learns, that matches these sort of natural innate processes in the brains? What if we could teach math in that manner? And obviously, that's very much the goal of Mind Research Institute. Grew out of research at the University of California, Irvine in the 90s and before, and building on the back of decades of prior research into this whole idea of let's look at the neuroscience, let's look at these fundamental learning processes in the brain. How can we utilize those to learn mathematics? And one of the outcomes of that research is the program ST Math, but really Mind Research is bigger than ST Math. It's looking at this whole totality of learning, if you like, and then thinking about, okay, what are some things we can do to facilitate that? And one of those is building this math program. But Mind really is sort of all about this shift in thinking. Now, I was a high school math teacher. I also worked for Los Angeles Unified, sort of a math director, math coordinator for quite some period of time. And during that time, both when I was teaching in the classroom and then out of the classroom working with teachers, this question of how do we teach preoccupied a lot of my thoughts. Is this idea of like, okay, how can I teach better? How can I sort of, help other people to teach more effectively? But I walked into a classroom 12 years ago, almost to the day, in fact. It was almost exactly 12 years ago. I walked into a room in South Central LA and saw 42 kids in a computer lab playing this game with a penguin. And I realized that someone, instead of asking this question, how do we teach? Someone had asked a very different question. They'd asked the question, how do we learn? And that was my first exposure to ST Math. And I realized that someone had really shifted the way they'd thought about this and then built something that was tapping into that sort of fundamental learning process. And I actually quit my job with LAUSD a couple of weeks later, and I've been at Mind ever since, building games, doing R&D on classroom programs and that type of stuff, and talking about what we do in presentations like this, which is always a lot of fun. So it gives you some of the background as to sort of, here's the how, here's the why. So now that we've sort of seen that, let's play a game. And again, I'm going to have to bring up the chat window at some point. Besides, this is where I really miss seeing everybody's faces, but we'll survive. All right, so I'm just going to assume that everybody is happy and smiling and enjoying everything. And I'm just going to have to go with that and roll with it and hope that that's what's happening here. So we're going to play a game. And this is a game you might well be familiar with. Don't worry, we're playing a lot more than just this, but we're going to start here. And this is a game that's really is about spatial reasoning, fundamental core to ST Math. Obviously, the ST in ST Math is spatial temporal math. This game kind of epitomizes that type of thinking. This is something that we can get kinder, first and second grade students to solve. Now, they don't necessarily start with something with 3 sort of moves like this. They start with something a little more simple. We build them up to it. But for you guys, we're going to drop right in here at this slightly more complicated level and see how we go. So notice there's no language on the screen. The goal is pretty simple. Here's Gigi. Gigi's kind of feet up, pointing out of the screen. And we need to figure out in 3 moves, how are we going to get Gigi across the screen to kind of look like this so Gigi can walk off the other side. And the moves are these things down here. We can call them 1, 2, 3, 4, 5, and 6. We can repeat them. We can do whatever we want. Getting stuff wrong is awesome. It's always good to get things wrong, because when we get things wrong, you'll see kind of just how much of an exploratory thing this is. Let's just bring this up here. Okay, fantastic. All right, so let's see if anyone wants to give me some moves. What do you think we should do? How should we get Gigi across the screen? So you can call them 1, 2, 3, 4, 5, or 6. So you can either give me 1. Oh, very good. Okay, all right. So I see various things here. It looks like everyone's got the same starting point. Okay, so let's see. 2, 3, 3. Fantastic. Let's give this a go and see how this works. Okay. Are we smarter than second graders? All right, let's test it out and see. All right, fantastic. Gigi got across the screen. So before we get too excited about this, let's up the ante a little bit. So this is the same puzzle. There are actually multiple ways of doing this. Yes, so well done, well done, Scott. Let's make this a little bit more tricky. Let's give you a starting move. So now I've put move number 5 in. Now, when I do this, what I normally see is I see people starting to move their hands, because now you've really got to think about it. The move 2, 3, 3 is a fairly common way of solving this problem, which is great, totally fantastic. So now there are actually 12 different ways of solving this. So let's see if we can think about it a different way. And let's just try what we call like a waterfall here. So what I want, don't type anything yet. So I want everyone to think about what this second move should be. And when I say go, I want everyone to enter a number in a minute, and we'll see what we get. Okay, so just take a few seconds to think about what this second move should be. I've put move number 5 in. What do we think the next move should be? So we're going to count down from 5. 5, 4, 3, 2, 1. Okay, enter in. Let's see what we think. All sorts of different things. Okay, fantastic. So I see lots of 5s and I see lots of 2s. Now, what's interesting is there are actually 2 different possibilities. Let's go with one of them here. I'm going to stick in 5. Let's do that. So we'll come back and we'll see if the other one would have worked. So I saw lots of 5s, and let's do that waterfalling again. So now let's think about it. We went, we've moved that. We've moved 2 moves. So let's think about what this third move should be. Same deal again. I'm going to count down from 5, and then I want everyone to type something in, and we'll see what we get. 5, 4, 3, 2, 1. go. Okay, let's see, what do we get? Tons of 2s. All right, everybody is on the same thing. Wow, you guys, your spatial reasoning is either brilliant or we're all completely wrong. So now let's just have a little look. What do we think? Have we really got these second graders beaten? Oh yes, you guys are just too good. All right, fantastic. And just for completeness, I know there were a lot of people who, after I put this in, you said we should make 2 the second move. So just for one more time, what do we think the last move should be in this case? Let's see, let's give it, we'll just take a few seconds to think about it again. I'm in waterfall. 5, 4, 3, 2, 1, go. What do we think this last move should be? Oh, you guys are just way too good. All right, fantastic, good. The spatial reasoning skills are strong with this group. Very good, fabulous. So notice lots of different ways of solving this problem. So let's just have a little look at what's happening here from the neuroscience perspective, because you guys engaged, you actually got it right every time. We'll also discuss what would happen if you got it wrong. And also push something else that hopefully might be a little bit more complex in a minute, and you'll get that chance to struggle a little bit more strongly. But let's look at what is happening here from a neuroscience perspective. And what we've got going on is something called the perception action cycle. And this is not something that mind research created. This is a well understood piece of neuroscience, and it's something that every single human being has available as a sort of feedback mechanism within our brains. In fact, all mammals use this perception action cycle on a daily basis. It's something that, again, is sort of, it's an innate learning mechanism, and we can tap into that and use it to build learning tools, to build, learn things like fraction numeracy and so forth and so on. But really, it's a survival mechanism that sort of is fundamentally part of being a mammal. So let's have a little look at how this works. So anytime we're confronted with a problem, doesn't matter what that problem is, and in this case, it's something as sort of abstract as how do we get a penguin across the screen? Once we understand and see what this problem is, we basically make a prediction. And to make a prediction, what happens is in our frontal cortex, we have schema, we have ideas, concepts, things that we understand, neural networks that we built over time. And they exist and they fire up. And one of those schema is going to win. Our brain is going to go, yeah, I think that's the way to do this. So one of these schema is going to fire the most strongly, and it's going to make a prediction. And then based upon what we predict, we're going to take some action. And notice this was the first set of moves that we tried, and it was correct. And the game is just going to animate out whatever it is we tell it to do. It doesn't say right or wrong. It's just we get to see exactly what happens. And now, again, we perceive this. And this is where it gets interesting from a neuroscience perspective. In the brain, we have a little thing called the hippocampus. It's like 2 little seahorses, one in each hemisphere, right in the middle of the brain. And the schema that fired up to make the prediction is held. The vision of that, if you like, if here's what I think is going to happen, is held in the hippocampus. And now along comes our perception of here's what we see happening. And in this instance, these 2 things match. Here's what I thought was going to happen. Here's what actually happened. Boom, they match. And now the hippocampus sends out a signal to that schema. It says, well done. And it rewards it by making it bigger. It literally grows it. So this means that every time we engage with a problem, if we get something right and we're observing this feedback, we're literally growing whatever the schema is that we're trying to build. So whether that be fraction numeracy, spatial reasoning, as in the case of the problem that we were just working with, by solving the problem and getting it right, we're getting this feedback that literally makes that schema bigger and stronger. So it makes us more capable of solving problems, right? So that's how we kind of build in that sense. But we don't only learn when we get things right. So my son, who's now in 5th grade, had heard of this idea about we learn through mistakes, and he was saying, so what? Like, every time I make a mistake, I'm learning. And I'm like, no, it's not quite as simple as that. So Joe Bowler very definitely onto something with this idea of learning from mistakes, but it's not just a question that we learn by getting stuff wrong. The key comes if we are engaged in this kind of cycle where the student is making the prediction, taking the action, observing the outcome, and kind of thinking this through. If the student is engaged in that and something does not work the way they thought it was going to, then yes, the learning potential from that is huge. So basically, if the student is the one who is doing the doing, then the potential for learning from mistakes is big. Watching somebody else make mistakes, not so much. Just making mistakes without any meaningful feedback, not a whole lot of learning. So it's not a question that just mistakes equal learning. Mistakes equal the opportunity for learning if, as a student, you're engaged in this kind of cycle, which is where this game-based learning, of course, is so powerful, because it's not too difficult to get students to engage pretty strongly and feel quite invested in trying to get GG across the screen. So once they've invested in that, once they're kind of committed to, I want to get GG across the screen, then we can get them heavily engaged in this cycle. And now they can learn, obviously, and grow their schema when they get stuff right. Similarly, as we see, a very similar but slightly different process happens when they get something wrong. So in this case, they see the problem, they make a prediction, they take an action. Let's say they've made moves like this. And the key is that the game animates out whatever they put in. It doesn't tell them whether it's right or wrong. They get to see, did Gigi make it across or not? And if not, why? And then there's that same before perception into the hippocampus. And in the hippocampus, it's holding, here's what I think is going to happen, and now here's what did happen. And in this case, they do not match. So now the hippocampus sends a very different signal to the schema that made the prediction. It says, that was not so good, and it deprioritizes it. This is how to help students address misconceptions. So obviously, right now we're dealing with sort of learning loss, learning recovery, whatever different phrases and terms you want for it. But it's very tempting to sort of try and address those types of things and all kinds of remediation by just trying to gap fill, by saying, okay, what do the students not know? Let's fill in some gaps and hopefully that'll get them through. But for the most part, students end up with significant misconceptions, especially about subjects like fractions. And you can't address that by just telling them some stuff and hoping you're going to fill in the gaps. You really need the students to engage in this process, to test out their misconceptions and see for themselves that they don't actually work. And then gradually through that process, the schema that is the misconception is gradually going to get diminished and replaced with sort of, ideas that are more correct. Because what happens with the hippocampus, when you get something wrong, not only does it sort of weaken that schema, it sends out a second signal that basically says to the brain, you need to learn something new. So this is a powerful fundamental learning process. And it's not the only one. This kind of perception action schema building is obviously part of every single puzzle in ST Math, but there are other critical sort of learning mechanisms in the brain, and we're not going to dive into all of these, but another big one here is this idea of academic discourse. And in this sense, we're not talking about just learning some academic language or using academic language. The real power of academic discourse in terms of students building schema is having kids try and express things in their own words. When you get kids to try and explain that thinking process, that's just literally the act of having to explain is a huge connecting sort of schema building activity for kids. So getting a class, for example, using a puzzle talk, which we have in ST Math, getting them to discuss as a group how to solve a problem, hearing how other kids are solving or thinking about the problem, all that kind of stuff. These are powerful learning mechanisms that once the students have the schema, once they have the ideas, then sure, you can attach academic language to those specific ideas. But the idea of academic discourse really kind of comes before the academic language. You want kids talking about it in their words, making sense of things for themselves, and then we can add the specific language on top of that. So there are a lot of these really critical learning processes in the brain, and they're utilized by ST Math very explicitly to try and build schema, to build conceptual understanding and help students. All right, time to play some more games. So what I'm going to do is I am going to push this QR code here. If you have a cell phone, hold it up to the QR code, and you know what, let me just get the chat window open here. I'm going to move it. I know it covered it for a second. So, and then what if you should pull up a game, and you might get a little spinning GG for a moment, but if you can type in the chat, can you just type in, say, yes, or got it, or something, if it works, right? So okay, good. Thank you, Kayla, good, okay. So, all right, fantastic. So it looks like this is working for most people. I say GG might spin a little bit, don't worry about that, but it should. It also, if you turn your phone horizontal, I think you'll have more playing area. Okay, good. All right. So I'm not going to tell you a whole lot apart from the fact that, you know what, you can drag these things, and I'm going to leave you explore and see if we can figure out, or if you can figure out, how to get Gigi across the screen. You know, you can't even see Gigi at this point in time. So I can't hear dings, unfortunately. I did play this game with a room full of actual people in person this morning, which was a lot of fun because I could hear the dings and I could hear the non-dings as I was walking around the room. So I'm just going to have to imagine what's happening. But let's see. And maybe what you could also do is, let's say once you reach puzzle, the real interesting puzzles here are 4 and 5. So once you reach puzzle 4, if you could type a 4 in the chat, and then once you get to puzzle 5, type in a 5, and then once you finish, type in done or something like that. So I can sort of get some sense. Yeah, you could try using Safari, I know. So just as a caveat here as well, ST Math is not designed for phones. Students will not play ST Math on phones. It does work on phones, kind of, and you know, like different depending on the browser, it will generally work. Sometimes we might run into some problems like this. So if you can't get it working, don't panic, just hang tight for a minute, and we will play it together once we're done. So but don't think that this is the ST Math experience for kids. It's not. This is not how it's designed. It's just, it's very useful in presentations to be able to have people scan these things. If you have an iPad, you could try using that. That would do the same thing. But it should generally run on Safari. And it's not that Chrome isn't supported, it's that Chrome on phones is not supported. So it should work just fine on iPads. And like I said, if you want to type in the chat any kind of progress you're making, that would be great. Okay, all right, Kayla, gosh, rocking and rolling. Okay, in the meantime, and if you finished, or once you finish, think about what mathematics was involved. Ooh, okay, there you go, Kathleen, you're jumping the gun, but fantastic. So yeah, think about what mathematics was involved at the beginning, and think about what mathematics we got to by the end. You don't need to type that in the chat yet, but typing in progress would be great. In the meantime, I'm just gonna see if, here we go, I see the video panel. Okay, it just helps me to see people for a minute. Complete, all right. Okay, yeah, sorry, Mary, it's, as I said, this is not necessarily a perfect presentation moment, but hopefully we can get enough people to do this. So let's just take another minute and then we'll work through this together and see if we can kind of get this going. Okay, I see lots of studious faces. Very good. Okay, anybody else done? Okay, very good, very good. Let's take 30 more seconds and then we'll debrief this together. Standards for mathematical practice. 1, 2, 3, 4, 6, 7, 8. Okay, but not 5. All right, okay, very explicit there. Okay, fantastic. Yes, definitely plenty of seeing structure going on here. Okay, awesome. So I think I'm going to dive in and work through this together. So this is going to be a little bit less interactive in terms of a discussion than I would normally be able to do, but in the interest of time, I'm going to sort of work through this and hopefully we can kind of get in this together. Okay, so let me get rid of the chat. Well, I'll keep the chat here actually because I'm going to use it. So let's see. Hopefully you can see enough of my screen. It's not being covered up by too many things. Let me get rid of this for a second. Okay, so the first puzzle, I'm sure most of you kind of figured this out. And so fantastic. Okay, great question. So if we don't know where to start? This is a very good question. So what do we do? So in this case, you can see if I click on the screen, and this is true in anything in ST Math, you'll see some things start flashing. So here, this is telling me like, okay, these things you can do something with. And you can see as soon as I touch this blob, the sort of the space around the number line lights up. So let's say as a student, I really don't know what I'm doing. So I'm just going to drag this thing here. I'm just going to, looks like I can put them on the number line. So let me just do that. Remove this chat window. And this is what students do. They poke around and they just try. And in this case, I have no idea what I'm doing. Let me just see what happens. And oh, okay. Okay, so somehow those things can't fall down. Now I noticed that the ones I put on 4 and 5 fell down, but the one that I put on number 6 didn't. So I'm sure most of you kind of had a similar type of thing where you kind of go, okay, I think I get this. And I see a lot of people putting, you know, this is obviously sort of multiplication and so forth and so on. So this is something really from 5th grade and above. So this is not like, it starts off very simply, but this is definitely something where kids would be, you know, relatively comfortable kind of poking around with this. So, okay, so now we can see we've got this kind of skip counting thing working its way down the line. Now, also, I hasten to add, this is also a demonstration sequence. Kids would not be pushed through a sequence that ramps this quickly. This is something that enables us to talk about the learning path that we're able to create, but this is not a sequence of puzzles where students would go in 5 puzzles from something that started that simply to something that ends this complicated. So this is very much let's look at this sequence so we can think about how we can build learning paths, but don't get the impression that kids would be expected to sort of make these leaps this rapidly from one puzzle to the next. Okay, so that's a good point there. So, okay, so now let's say, okay, we can see we kind of get the idea. We've got this thing, it's going to skip count. This time we can see there's, you know, a gap of 2. So, okay, I'm going to put these in place and let's see what happens here. And I think, actually, I don't know if anybody else tried this, but I think this is going to work too, right? As long as I get it in a place. Okay, okay, so as long as I get them to land where this thing lands, looks like we're good to go. All right, so now puzzle 3. This is where things starting to get a little bit interesting. So obviously, I'm sure some of you probably did this, which is totally fine. We would start off maybe trying something like this. What was wrong here? What was tricky about this? What was the interesting thing that happened? Mathematically, what is this starting to do? And did anybody get, I'm sure some of you got past this puzzle. What? Skip the 4. Why? So, yeah, so, okay, so now we're starting to number the steps, okay? So we started with this thing where really it's just skip counting, and now it's kind of like numbered skip counting. So we're having to think about how many iterations, absolutely. And of course, if we didn't see that, it's fine. We get to test it out, we try it, and we see, oh, and notice I can pause, students can pause this, and we can see, aha, as it did this, this became 4, which didn't match the 5. So, okay, I need to do something a little different here. So now we're going to put this 2, this 3, and this 5 is going to be on 10. So we're basically kind of numbering the skip counting. This is obviously some kind of sequence. And then we get to questions that really start to push it out a little bit. Yes, there we go. I don't know. Like I said, students would play lots of puzzles at each level, right? They'd be a really explicit kind of like, okay, you're moving to the next level. So it's a little easier to kind of trigger that. Now notice something different. This is intentionally designed as a sort of a chance to work with teachers or whatever to kind of dive in and see, let's think about the learning path, think about the bigger picture of what we're doing there. And also I only gave you a few minutes to do this. And of course you're working remotely as opposed to being in a room together, where very often that cross-pollination of ideas really helps everyone to start doing something. Okay, so where do I need to put this 6? Where should this go? What do we think? And how about why? Where do I need to put this number 6, and why should I put it there? So Scott, you're absolutely right. It's going to go on the point 19, but can somebody explain why does this? Okay, that's a very mathematical explanation. Anybody? So where do you get those numbers from? I see 3 times 6 plus 1. So where does the 3 come from? Where does the 1 come from? Where are you getting those numbers from? You're absolutely 100% correct. Kathleen, It's the 6th 3, and everything is shifted to the right one. You're absolutely correct. The 3 is the length of this little pattern thing that's going to waltz its way down the number line. So we're skip counting by 3s, but notice that we're starting at 1. So absolutely fabulous. There you go. So we get this thing and boom, 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 boom. So before we get to this last question, what's different? So this question right here, of course, is really where the rubber meets the road in this instance. What's different about this particular question? What's the challenge that we're sort of pushing out right here? Because this is suddenly a whole leap different, right? This goes somewhere very different. So I guess there's 2 questions I have. First of all, mathematically, what is happening here and what makes this question so interesting and challenging and different from the one before it? What do we think? So it's not starting at 0, absolutely. You lose, okay, fantastic. Marie, really, really critical point here. And Kathleen, same thing. The whole point is you cannot actually see where this goes. Jennifer, you're totally correct. This is literally moving from, okay, I can kind of, you know, like with the last one, I can visually kind of skip count down the number line. Whereas with this one, I can no longer do that. It's going to go off the screen. So you really, as a student, you have to understand what is the pattern, what's happening here, how does this work? And they have to kind of project their way through. It's like, okay, so this is going to happen 9 times. The difference between these, I certainly 7 minus 2 is 5. Absolutely, the sort of the amount that it's growing each time is 5. It's going to grow 9 times, but it's also starting at 2. And obviously, I think most of you probably would have gotten that this is going to get to 47. Now, I actually tested this with my son who was in 4th grade at the time, and he figured this out. He went through this whole sequence perfectly fine. It took a while, and it was definitely quite a struggle. But what was so fascinating was I had him talk to me about how he solved it. And first of all, what mathematics is this really getting at? What mathematically, what's happening here? What's the sort of things are we doing? So obviously there's skip counting. Yes, there's multiplication. What is this really getting at? And what would this be a really good sort of thing to have kids do as they're starting to explore something? Yeah, multi-step, absolutely. So expression, division with remainders, math using parentheses. Yes, to all of that. There's something, the first one there is kind of closer to it. Order of operations are a piece of this. I wouldn't say that's the definitely number patterns. Yes, absolutely. This is really basically linear equations. This is a linear situation. Absolutely. 9x plus 2 is equal to 47. That is exactly what is going on here. This is a way to get kids to think about linear situations, for example, but they can do that thinking without even having to know about the equations. So my son, who was in 4th grade, figured this out, and he was able to talk about how he did this last question. Like, okay, it's 9 times, you know, he didn't use any of the language of algebra, but he used his own words to basically talk through algebraic thinking. And this is one of the powers of this type of game-based learning, is that we can get kids doing the algebraic thinking or whatever thinking that we need them to do without having to sort of teach them the language first. They can understand it in their own terms and then add the language on top of that. So, okay, fantastic. And yes, this absolutely is a model of, actually this would be 5x plus 2 equals 47. The 9 obviously is the x in this case. Okay, fabulous. All right, so let me just take a little bit of a check on time. I'm trying to remember, actually, are we out of time, Chanel? We do know that math language is very weird.
Nigel, we have about 8 minutes left, and then for this question, your chat box is in the way of the answer choices, just so you know.
Oh, yes, yeah, no worries. Okay, 8 minutes, oh, tons of time. All right, fantastic. I am so out of my element without having multiple screens. One little laptop screen is so limiting, but we're getting there. All right, fantastic. So let's we'll do this real quick, and then we'll talk about some bigger picture stuff as well. So of course, it's also totally possible to use this type of learning methodology to build some of the real critical building blocks for students, like, for example, things like fractions. So this is a fraction question that was on the NAEP assessment. It's also been the subject of many research papers because students didn't do very well on it. Only about 1/3 of kids in 8th and 12th grade got this correct. And the challenge here is this looks like it's a fraction addition question. And in fact, when you present this to a lot of kids, they will start doing something that looks a little bit like this. They will throw down some procedure and start trying to cross multiply. It may or may not involve a butterfly. The problem is that even if you do that correctly, you end up with this. And that's if you get the numbers correct, and they're intentionally chosen to be quite large. The problem is, of course, this still doesn't look like any of these answers, because really this isn't a fraction addition question. It's a fraction concept question. It's basically saying to the kids, do you understand what a fraction is? And only 1/3 of them were able to basically say yes. So if you understand what fractions are, this is easy. You look at 7/8, you go, it's about 1. You look at 12/13, that's about 1. Estimate, 1 + 1 is 2. But of course, if you don't, and you get stuck in the procedure, and most kids here answered C or D, they added across the top or the bottom, it becomes very difficult. So this is another thing we're able to do with ST Math very powerfully. We're able to give kids that ability to visualize these concepts and then start to make that kind of number sense around things like fractions, for example. And in this case, we can use a game like GG Cycle, which is all about helping students to basically map these kinds of things onto the number line. So in this case, notice again, this is another sequence. Students would play a lot more puzzles at every single level. We're just zooming through and looking at the learning path of how we're able to build this kind of understanding for kids. So, okay, we're starting really simply where we see Gigi on some wheels, and all we've got to do is figure out how do we get Gigi to the basket, right? And then gradually we're going to ramp the complexity up. So now we no longer have whole number pieces. This is obviously not 0, it's not 1, it's somewhere in between. And as we go, we can gradually increase the difficulty. So here's a really little piece of wheel, and then we can make a big lift where now we're working symbolically. Everything started off purely visually, but now we can no longer solve this puzzle without thinking about the symbols. And in this instance, the students would have played a lot of puzzles to make those connections, but now they have to use that symbolic reasoning. So again, notice we've moved from the concrete to the more abstract, and we continue to do that. So okay, we're at 1/3. I'm gonna move pretty quickly through this so you can sort of see the idea of how this type of learning path works, and then we'll get to some questions and stuff at the end. And now we can ask the question backwards: how many halves do I need to get to 2.5? So you can see this type of game can really build this fraction number sense for kids, to the point where we can get them working symbolically, and in this case, they're basically graphing fractions on a number line. And we can get them to add things together. So here we've got a bunch of 8s. And now we can get to questions like this. We've got 2/3 plus 1/3. And okay, so that's going to give us 3/3, which is 1. And then we can get students here where we can now add fractions with unlike denominators. We obviously have games that are explicitly going to do that in terms of the whole process. This is about estimating. Do I know where a half is? Yes. Do I know where 3/4 is? Yes. Okay, so you can put them together. We can add these fractions. And of course, we can get kids all the way to something like this, where they can go, yeah, 7/8, that's about 1, 12/13, that's about 1, put them together, and I'm going to get somewhere close to 2. So we can use this process to build these kind of reasoning abilities for all kids, for all of the mathematics ideas that are really critical. And I'm going to zip through some of this and get to this sort of critical piece here. This, I think, sums up what we do in a big way. So it's good, it's a good thing to think about the types of mathematics that kids need to do in terms of a chart like this. You might be familiar, it's called a quadrant D chart or a rigor relevance chart. And it's really saying, what type of thinking are students being asked to do in the math classroom? And what type of problems are they being asked to solve? And the implication is we want students working here using creative thinking to solve non-routine problems. The challenge is that a lot of curriculum materials obviously fall well short of that. And many people, many teachers and many parents, their entire experience of math is in this bottom quadrant, where it's basically tell you how to do something, do a lot of routine practice, and for many people that is math. And what we're able to do with ST Math is we're able to give all students access to this space. As you've seen from pre-K onwards, we can get them thinking, solving rigorous mathematical problems, and thinking in that sort of mathematical way, sort of out of the box and problem solving, which is a big deal. Okay, a couple of closing thoughts. I'm sure everybody's seen some version of something like this, where we've basically got this dichotomy between procedural and conceptual learning. And I'm sure everybody's probably been asked a question, something like this, from a parent at some point in the last couple of years. My son went to an after-school pod with 3 families that we knew really well, and every single parent in those families asked me this question or some version of this question at some point. And there's often a big misunderstanding of, why are we even learning mathematics? Why don't we just teach these procedures and get kids quickly to the end zone? And, you know, we see a lot of memes like this as well, where it's a real misunderstanding of, why are we learning math? We're not learning it necessarily for the specific little tiny little bits of the curriculum. We're learning it as a system of thought, of the ability to sort of think critically. And I think one of the best ways of sort of putting that all in context, can anybody tell me, here's a picture, this is from the 40s. Can anybody tell me, where are the computers in this picture? Anybody type in the chat, where do you see the computers? The people, fantastic, thank you, Kathleen. So yes, this is a picture from the 40s, human computers. And you may well be familiar with movies like Hidden Figures, for example, where you know, we saw at NASA the value of human computers and so forth. So brilliant film. And what's interesting is when you look at this quote from 1942 from NASA, as it was called then with a C, the volume of work often necessitates computers who can perform the routine machine operations with great speed, but who need not have much logical insight into what the result should be. So the point is here, not that long ago, there was a need for people to be really good at procedural mathematics. My mother was an office manager back in the sort of 70s and needed to do a lot of, you know, calculations and procedures as part of her job. How many people are employed today to be good at doing procedural mathematics? And again, we can just type that in the chat. What do we think? How many people have a job? None. Absolutely spot on. And times have changed, but the one, Alexa, there you go. Yes, and actually, don't get me started on the subject. You can find where Alexa and Siri actually have different answers to things. Ask them what 0 to the power 0 is, and you can have a lot of fun with that. All right, so so the interesting thing, but this is when our textbooks were written. This is when traditionally, that's when a lot of the thought about how math class should look came from. And if the old way of teaching was about getting kids to do mathematics like a machine, what we need to do now, and obviously what ST Math is all about, is we want to build that understanding, because the kids are going to be the ones who are going to have to build the machines. So I think I'm going to zip right through that. You may have seen this research, which is awesome, showing that actually ST Math had this huge impact on kids' self-belief about themselves as mathematicians. But I think I'm going to stop it right here. So thank you very much, and see if we have any questions before we have to finish. And Shanaz, I don't know how many minutes we've got, probably not many, but
I think we are just 1 minute over, so that was amazing.
Oh, there you go.
But thank you so much, Nigel, for the wonderful presentation, and thank you for everyone who joined this session. Please see the message in the chat to post on social media with the wonderful things you learned with Nigel today. And make sure within the next, I think, 4 minutes, we've got our session starting for a customer panel, a session on data, discourse, and then problem-solving process. So enjoy the rest of your day.